Everybody, good morning, and thank you for joining us today for our commercial heat pump water heating class on multifamily. My name is Romano Bardillo with the Lighting Design Lab, part of Seattle City Light. Today we're going to have Colin Grist from Ecotope presenting today, and Lauren Baskar as our moderator. Just thank you everyone for joining. If you've joined us before, you'll know that you're all going to be muted, but please engage with us on the bottom right-hand side of the GoToWebinar dashboard. There's going to be a chat feature you can access, ask questions, comments. There's also going to be a couple of engaging polls from an app called Slido, so please engage, making this a little bit more interactive. As questions come up, we'll have some purposeful times to answer them, so please engage. And now I'm going to leave you all with Colin. Thank you very much again.
Great, thank you, Armando. Welcome again, everyone, to a training on commercial heat pump water heating systems for multifamily residents. My name is Colin Grist. I am a mechanical engineer from a mechanical energy and plumbing consulting firm in Seattle known as Ecotope. I've been with Ecotope for 8 years, working both on high efficiency mechanical systems in buildings as well as plumbing systems. And today I'm here to talk to you more about those plumbing systems, specifically commercial heat pump water heating systems. And Ecotope has had a lot of experience over the last decade or more with these commercial heat pump water heating systems. And we've learned a lot through various case studies and research projects all about these systems and how they interact and save energy in our buildings. And so I'm here today to share some of those lessons with you and highlight some of the key features and great things about these commercial heat pump water heating systems we have. Today, we're going to discuss commercial heat pump water heating systems with kind of 4 topics. We're going to look at the potential for energy savings. That's one of the primary reasons to implement this technology in your building is it will dramatically reduce the energy use associated with the domestic hot water load. And in residential buildings, we'll see that that domestic hot water load is very substantial. And so there's an enormous amount of potential for energy savings simply by implementing one of these heat pump water heating systems in the building that it's serving. We're also going to talk about the various products on the market, how we refer to these products, and some of the applications that they're best suited for. We're going to try to break down some of the barriers around how we speak about these products so that you're familiar with the terminologies and can approach various manufacturers, plumbers, or other design professionals working with you on your projects. Then we're going to talk about the 4 components of a commercial heat pump water heating system. And these are also the same 4 components that are in our residential heat pump water heating system, and arguably the 4 similar components that are in our gas or electric resistance commercial water heating systems. We might not think about them as 4 independent components all working together in those gas or electric resistance water heating systems. But they are. And so commercial heat pump water heating systems will define those 4 components. And in later webinars, which we'll show you a few at the end, we dive into a lot of details about those components and discuss individually what you need to be attentive to and what considerations you need to be aware of when you're working with these commercial heat pump water heating systems. And then the last thing is everyone loves case studies. And so we're going to show you a case study that's a new construction building here in Seattle, Washington. And so I hope you'll join us for the entire presentation today. And we got about 2 hours to go over this material. So a good amount of time, but there's a lot to cover. And so we'll just cruise right through it. But please, if you have any questions at any time, you can ask those. And we have a few ways to ask those. Lauren is going to be moderating today with DNR International, and I'll let her introduce the Slido here.
I'll be looking at the other screen. Hi, everybody. Yeah, so you're going to need your smartphone today. we run an app called Slido. The great thing about Slido is it doesn't take any personal data from you. So it's very clean. You log on today and then you'll log off, and they won't get any spam after the session. So today we'll have you enter the code. It's called Multifam after you go to slido.com. And that way you'll be able to participate in some of the live polls that we have today for you. The other thing to note is there is a question and answer tab on the GoToMeeting chat bar that you see here on the menu. And that's a way for you to send questions throughout the session this morning as you have them. I always like to enter my questions or comments as they occur to me instead of waiting. And what I'll do is I'll get those, read them here to Colin and have Colin respond. So we always enjoy your interaction. So get ready with your smartphone for the Slido app, and also feel free to enter your questions as they come to you or comments in the GoTo Q&A function. Thank you so much.
Great, thanks, Lauren. So you can get to Slido via web browser, slido.com, or if you're on your smartphone, you can take a picture of this QR code here, and that should bring you to the page. And our questions today, we have a few of them, but we're looking to understand who's joining us today. This is a virtual event, of course. I have no idea who's in the audience today, and so it'd be great to understand if I'm talking to a bunch of architects, a bunch of developers, a mixed bag of construction folks and architects. Who's out there that we're presenting to today? It's really helpful, and we can better suit this presentation for that audience. So it looks like we have a few people that have filled out the form or the Slido so far. We have some engineers, great. Mechanical, plumbing engineers, you will be specifying and working with these systems. You might have had some experience in the past, but with the recent, or with the code, the 2018 Seattle Energy Code going into effect shortly, we're going to see that the commercial heat pump water heating systems are required for multifamily buildings. So you might be working with these more in the future if you're working on that type of building. Building electrification enthusiasts, yes, we want to electrify our buildings. Gas is not the greatest thing in the world. It has some good qualities, but it also has some challenges that come with us. And it's really important that we move to electrify our buildings to better future-proof us for the future, of course. And then HVAC manufacturer out of New York. Great, thanks for joining us from the East Coast. Energy program consultant, great, you're here. It's really important that we all understand how much potential there is for energy savings with these commercial heat pump water heating systems. We have a plumbing inspector and energy analyst. I'm assuming most of us are from Seattle today, as this is presented or hosted by Seattle City Light through the Lighting Design Lab. Then how experienced are you with these commercial heat pump water heaters? Dabbler, not an expert. I think most of us are in that category. We have a couple beginners and no all-stars here today. This course on central heat pump water heating for multifamily residences is a very high level course. And so we're going to discuss these systems at a very high level. And we do have other courses that go into much more detail on system configurations, different heat pump types, refrigerant selection, sizing, a whole world of the engineering behind getting these systems implemented into our commercial buildings. And what questions do you bring with you today? How to most realistically estimate the recirc loads, in particular for energy modeling applications. Yes, so in commercial buildings, we typically circulate water through the hot water distribution piping to keep that water hot at the tap so that people don't drain as much water out of their hot fixture when they're looking for that hot water. And so that recirc system adds a load, and that load can be problematic for certain heat pumps. And so it's really good that we understand that load in both how we are treating it and the scale or size of it. And so we can give you some rules of thumb for estimating that load later today. And then how to make this more accessible for affordable housing multifamily projects. Absolutely, heat pump water heaters do come with a little bit of a cost premium, and so we can consider through sizing exercises and through various equipment selections how to make our money really do the most for us, and we can discuss that a little bit today. So the first thing we're going to cover is why we're considering commercial heat pump water heating systems for these buildings. And there are some global, federal, and state policies that are driving this change. Seattle has some very great standards and great goals to really drive down the embodied carbon in our buildings and also lower the annual energy use of those buildings. And so those global and federal state policies are really driving some of the codes and standards that you and I as engineers or plumbing designers or developers commonly work with and refer to. One of those codes, specifically the Seattle Energy Code, is requiring commercial heat pump water heating systems for multifamily buildings and hotels in the future, starting here in a month, January 1st, 2022. And so we'll cover that shortly here today, but that is one reason why we're implementing these technologies in our buildings. And there's still opportunity, depending on where you are, to capture incentives and rebates. A lot of either federal policies or state policies or places like Seattle City Light or other utilities are still providing some levels of incentives or rebates for these products because they're seeing that they're saving an enormous amount of energy, but there is a little bit of a cost barrier still. And so they're trying to make that more favorable for all of us working in the field to get these highly efficient systems into our building. And then lower the operating cost. I installed a residential heat pump water heating system in my basement of my home here in Seattle, and it's been working fantastically for the past 5 years. It dramatically cut my water heating bill by a factor of 2/3. And we've done that both on the residential side and on the commercial side at Ecotope on many projects for the past 10 years or more. And so there's lots of opportunity to lower the operating costs here with these commercial heat pump water heating systems. And we'll show you how much you can actually save later today. And then as an energy efficiency measure, we pay for energy, so it's definitely lowering the cost, but we also want to conserve energy because as we progress as a society, we either have to be making new power plants or energy generation sources, or we have to be saving energy to essentially offset that requirement for additional power. And there is great potential to still save a lot of energy in our built environment, and that will reduce the burden on making these new, very expensive, high first cost energy generation power plants, whether they're nuclear or solar or wind or anything. We can dramatically save energy, which is really a source of energy if we think about it at a holistic scale across the US. And then societal changes. We'll see that, or many of us have read that gas water heating systems and gas appliances are creating issues, both in our environments and our homes and personal lives. There have been numerous articles recently in the past about gas cooking appliances and how they're leading to higher rates of asthma in children. And so there's a lot of reasons to move to a cleaner technology that's much more efficient, both in that residential cooking appliance, but also in the water heating system that is somewhere in the building you're working or living in. So there's lots of reasons to implement these heat pump water heating systems. But today we're really focused on commercial multifamily buildings. And so on the left-hand side, we have a pie chart of our baseline multifamily building. This is our baseline building in Seattle. And we have the various annual energy uses broken out. And so we have 25% of this pie is associated with heating water for domestic use. So there's a lot of energy over the course of the year that we're putting into water heating. The other, areas that we're putting energy into over the course of the year are consuming energy, our apartment lights and plugs, apartment HVAC system, our common plugs and lights, and our common HVAC, that's the garage exhaust system, our building ventilation system, and so forth. But we're focused really on this domestic water heating piece of the pie here today, because it's 25%. And if we implement a heat pump water heater, which is what this pie chart on the right demonstrates, we can dramatically reduce those two loads and save about 17% over the course of a year. And so we can dramatically reduce the energy consumptions of our buildings, which is why there's a lot of push and for the adoption of these much more efficient commercial heat pump water heating systems to replace our less efficient gas or electric resistance water heating systems. And there's technologies available, and they have been available for some time now. So this is a great opportunity for us all to move to a more efficient technology like a heat pump water heater and dramatically cut our energy usage down by a factor of 3. And so we learned that, there's societies driving these changes, there's global and federal policies that are driving these changes, and there's a large amount of energy savings we can achieve with this commercial heat pump water heating systems. And that's one of the reasons why the Seattle Energy Code has implemented a new code language that is requiring central service water heating systems be air source heat pump water heating systems, not fossil fuel or electric resistance, for the new construction buildings in Seattle starting January 1st, 2022. So just under a month away here. And those are for R1 and R2, which is multifamily, greater than 3 stories, or any hotel or motel occupancy. And so there's a lot of that type of building that we're currently constructing in and around the Seattle area. And so there's a lot of potential for energy savings here that will roll into the future year after year in these highly efficient buildings we're constructing. And this isn't a brand new thing. This has been proven. It's been implemented both in the Seattle area, in Washington State, and other colder areas of the US. Even on the East Coast, of course, where we actually get some significant snow. But this here is Sunset Electric. It's an apartment building in Capitol Hill, right by the East Precinct Police Station. And this project has been operational for at least 10 years now, and it's reduced there's a 70% reduction in the domestic hot water load. And so we show this bar chart down here on the screen, which portrays the energy, the EUI, or the energy use intensity, basically how much energy is going into that building over the course of the year, divided by the square foot or the total area of that building. And so it's normalizing for the size of our building. It's not normalizing for the occupancy, but it is normalizing for the physical size of that building. And so we can look at the 2030 baseline challenge, and we see that there's an EUI of about 63. So there's a lot of energy that's going into this building over the course of the year. We look at the Seattle mid-rise baseline, we have lesser cooling load, or we typically have. And so this is less. We have a very mild climate here in Seattle, and so that we're working with a baseline of about 39 or 40 there. When we built and constructed this building, Sunset Electric, we ended up reducing the energy to a EUI of 22. So a dramatic savings there, a reduction in energy use. And a lot of that was primarily associated with the domestic hot water heating load, shown as the light yellow bar on top there. And so this project, like I said, has been in operation for many years. It's been operating, it's been providing hot water to the occupants of the building. There's about 92 apartments. and it is using R134A heat pump water heaters located in an underground parking garage. And we're going to talk about that later when we're on the Jackson case study and how that all functions. But essentially what we're doing is, because it gets cold in Seattle, on occasion, we put these in a parking garage, and because that parking garage is underground, we get some geothermal buffering effect of that. And so we can keep the air a little bit warmer on the coldest days of the year, and that's going to help our air source heat pumps run on that coldest day along with the other days of the year. So we've proven that there's great potential to dramatically reduce the energy use in these apartment buildings. We've also done retrofits where there's an existing electric resistance or gas water heating system that was outdated, needed to be repaired or replaced. And so we implemented a heat pump water heating system here. This is the Elizabeth James House in Seattle. Once again, it's a senior low-income building. There's 60 apartments, about 61 tenants. And we utilized 4 stand-in CO2 heat pump water heaters that are located outside right on the front of this building facing 23rd. And this has dramatically reduced the energy use in the building associated with that domestic hot water load. And we're saving about $6,000, and some change per year, which equates to about $100 per resident in the building of financial savings, which is fantastic for these senior low-income folks as they, need to reduce how much their bills. We all want to reduce our bills, but there's more reason to do so in certain situations. So we've discussed so far that heat pump water heating systems, commercial heat pump water heating systems, can save an enormous amount of energy. It's one system that we're changing out. It's typically from a gas or electric resistance water heating to a heat pump water heater, and we can dramatically cut that load by a factor of 3, which is amazing because LED lights and other HVAC measures struggle to just get that vast amount of savings with one technology being implemented in our building. And there's codes and standards that are pushing for the adoption of these commercial heat pump water heating systems. And primarily they're pushing for them because we need to be either saving energy or building new power plants. And it's much more economical to be saving that energy right now than to be constructing new facilities to generate power. So in your opinion, what are some of the important reasons to implement a commercial heat pump water heating system for the buildings you're working on? Code compliance, yes, we always want to be compliant with the code, regardless of if it's Seattle Energy Code or a building code or a plumbing code. Once again, we can get back to the Slido. You can keep this open on your web browser screen or just take a picture of that QR code and it should bring you right to the page.
So Colin, I'll jump in here a little bit as people work on the Slido here. There's a lot of reasons to implement these commercial heat pump water heating systems. One of them is that with the new CO2 refrigerant, you can completely decarbonize your domestic hot water heating system.
Yeah, absolutely.
That's a big deal, right? I mean, that is for me, that is the #1 reason I love this technology.
Yeah, there's great opportunity there.
Yeah, great. All right, looks like we've got another person agreeing. I'm looking off to the side here because this is my second screen. Perfect.
Yeah, building points. We can get some code points, or if we're working with a LEED certified building, there's great opportunity to get points there to go up to that platinum level of LEED certification or whatever green building program you're working on. Reduce greenhouse gas emissions and future-proof infrastructure to the building. Yes, we're building these buildings hopefully for 100+ years, and so we're building them today, but we really need to be thinking about that future and what that future looks like and what energy sources they'll have during that time. Revel in modern technology, absolutely. It's like updating to the newest iPhone in a sense. I guess you could look at it that way. Great. Well, those are 4 great reasons. We'll keep pushing on. The next thing we're going to talk about is products on the market and what's available today and how it's delivered to the market. So we're going to first discuss a little bit of heat pump water heater language. And so we have 2 primary types of heat pump water heaters. We have the unitary or integrated heat pump water heaters, and these are typically residential products, but A.O. Smith does make a commercially sized integrated or unitary heat pump water heater. And this product has a heat pump, some way to control that heat pump, and a storage tank. It might also have a backup or electric resistance, and that you can see are these little bump ups right there for the coils. And so this is a great product, very similar to what I installed in my basement here to provide hot water, but they're typically residentially sized products. So they might not be the best suited for our larger commercial buildings, especially our commercial multifamily buildings that are greater than 3 stories. We have a significant water heating load with those buildings. And so these smaller, maybe a 80-gallon tank with a less than 1 ton or 12,000 BTU per hour compressor is likely not large enough for those buildings. But the unitary or integrated is the important thing to get across here, and that essentially means everything's packaged together in one convenient package. Split system, on the other hand, has some really great advantages. But primarily when we're talking about split system heat pumps, we're just saying that the compressor or the heat pump is separated from the storage tank. And that heat pump will still have some way to control it built into that heat pump water heater. And that might be relayed off of a temperature sensor that's somewhere in that storage tank. And split systems are more commonly available in commercially sized, but they also do come in residential packages. On the screen here, I'm showing the Sandin split system heat pump, recently rebranded as SanCo2, SanCO2. This is a CO2 heat pump water heater that is about 1.25 tons of heat capacity, or about 1,500 BTUs per hour. And this is a little bit larger than this residential product, and we can increase the storage tank or have various options with this, which is great. But this is still really a residential product that we can use in a commercial application. There's other manufacturers like Colmac, Nile, Mitsubishi, A.O. Smith, Rheem that also provide larger, more commercially sized equipment. And so that equipment might be 10 tons or greater typically. And so a lot more heat capacity there, but that's coming in the split system package with a storage tank being remote to the heat pump. And we also have these products being delivered to our market in 3 primary ways. We have the custom engineered system, which I like to use a woodworking example here, as I love spending time in the wood shop. This is the system where you go out, you chop down a tree, you plane or you cut, maybe bandsaw your boards apart, plane them down, joint the edges, rip them on the table saw, and then slap together that beautiful fine woodworking chair that you just made. And so there's a lot of engineering. You have to be trained in this. You need to be aware of certain things with maybe the wood characteristics or the heat pump, what you're using. So this is a great system. There's nothing wrong with it, but it typically just takes more engineering involved. And what we're doing here is we're typically finding pieces of equipment, a heat pump from one manufacturer, a storage tank from another manufacturer, but we want to make sure that the heat pump will work well with that, and maybe a backup electric resistance water heater from a third manufacturer. So all these are coming from multiple distribution sources and manufacturers. And so they can be more complicated, but we can have results, or we can result in a very high efficient, very, great operating, super engineered domestic water heating system. We can also look at more of the IKEA approach to making our chair, where we get all the pieces and they're already cut out, and we get our little Allen wrench and we can slap them all together. We still need a qualified plumber, of course, and some engineers for the sizing, but there's a lot of the little details that the manufacturer or the distributor is taking out of the equation here to help us as designers and engineers implement these commercial heat pump water heating systems in our buildings with very few errors, mistakes, or potential for things to go wrong. So here in our specified built-up system, all the pieces are typically separate, but they're coming from a single distribution source or manufacturer, and we're putting them together in the field. And so that is more of the IKEA approach to getting our chair. We also have the packaged skid system, and more manufacturers are looking to furnish these and make these that are already built up. Everything's assembled in either a single package or maybe two packages, so that this can be dropped on the construction site and hoisted up to either the rooftop of the building or maybe put in a basement mechanical room. But it simply requires the plumber, the electrician, the HVAC contractor to just connect up to this skid. They don't have to do all the piping because it's being provided with the storage tanks already connected to each other, connected to the heap up, and so forth. So this is one single package being delivered to the market that's easing the burden on a lot of the design professionals and engineers in the field, and also really resulting in repeatable and reliable domestic hot water heating systems that are super energy efficient. And I think that's what we all want, is low cost, but also repeatable and reliable systems that deliver that energy efficiency. And so we definitely have three very distinct ways to bring these products to the market. And myself at Ecotope have definitely been operating in this custom engineered world for the past at least 5 to 8 years. But I'm seeing more and more manufacturers and distributors pushing towards either these specified built-up systems, where they're helping you guide your selections on other equipment that's associated with that domestic hot water heating system, or they're providing a fully packaged skid-mounted system, which can be dropped in place and installed with much less field work, which has benefits as well. And then these systems, they come in various different ways. We can do a very custom system or a very packaged system, but they also come in different sizes, types, and configurations. We can connect the storage tanks differently. We can connect the heat pumps differently to get different configurations. We can also use different types of heat pump water heaters, a single pass or a multi-pass heat pump water heater, or heat pumps that use one refrigerant over another. And they come in a variety of different sizes as well. And so we might have a small commercial system that maybe this is serving like 6 to 8 units or 5 units in this example. And this might be a residential heat pump water heater in a closet with ventilation to and from it, coupled to a storage tank to extend the thermal battery we're working with. Or it might be 2 of these in parallel to serve that smaller commercial system. But we can also serve very large commercial buildings. And so this is the basement installation at Jackson Apartments, which is going to be our case study later today. And this is serving, typically around 250 units, where we have multiple large commercially sized heat pumps connected to multiple large commercial hot water storage tanks, as well as some backup heating equipment and a mixing station. And so we can have these very large systems as well as very smaller commercial systems. Both of these, depending on the building size, may be required by the energy code, of course. But when we're talking about commercial systems and we're talking about central systems, central doesn't necessarily mean one system for the entire building. We can have multiple commercial central systems. And so here is a project that is the Hope Workstation in Washington State. And here we're essentially using one of these stand-in heat pump water heaters coupled to a storage tank on the level below. So we have one heat pump over here coupled to a storage tank on the level below. And that's serving vertically 3 to 4 units, apartment units. And we do that multiple times. And because it's serving more than one residential unit, it's technically a central system. And because these are small residentially sized products, we couldn't serve 20 units with one of these heat pumps, but we can serve 3 to 4. And so this project we broke up into, I think there's 12 plumbing zones, and we're serving these vertically. It does mean more maintenance points, but it does give you some redundancy in your system as well, to an extent. And so these commercial heat pump water heating systems, you may be thinking that they have to be this large, really expensive built up system in the basement, but there are opportunities to really cut first cost and do smaller systems that are serving smaller zones, even in our big buildings, or specify residential equipment for smaller residential buildings instead of putting the larger commercial equipment in those smaller projects. So we have a few basic, really high-level case studies here, or conceptual studies. And what I'm showing here is 2 integrated heat pump water heaters with the heat pump on top and a control system and a storage tank below with some backup elements shown there. And so these 2 connected in parallel work in tandem to provide that higher heating load we might see with these larger buildings. But once again, this is really using the residential unitary equipment, and it's more suitable for smaller buildings. It's also really great for commercial kitchens or other restaurant environments that have a water heating load. Restaurants definitely have a significant water heating load, and it's typically associated with the time of cooking. Kitchens also get warm. If you've ever been in a kitchen, whether it's your kitchen at home or a commercial kitchen, they get hot, and heat pumps are taking heat out of the air, putting that heat into water and discharging cool air. And so we can discharge that cooler back into the space in our restaurant or our kitchen environment and cool those chefs and cooks in that kitchen, get some level of free cooling out of our heat pump technology. So these integrated package units are fantastic for this type of application, whether it's a restaurant kitchen or a Costco kitchen environment or a grocery store. Those typically all have a cooling load, and we can basically recycle or do double duty with our heat pump to address some of that load to keep these folks in the kitchen a little bit cooler and still provide really high efficient water heating to the project. But we're really focused on multifamily here today, so I'll go back after that short tangent to another example. Here we have boutique apartments in the Yesler development area. You can see the Port of Seattle back there, the Seahawks and Mariners stadiums, excuse me. And this is using commercial heat pump water heating equipment in a very custom engineered system. Here we're using Colmax, and this is one of the earlier generations of their product. Their product has changed and advanced since this design. But we have essentially 2 primary heat pump water heaters here, coupled to a bunch of storage tanks, and then a dedicated heat pump to do the temperature maintenance heating system. We're going to briefly touch on the temperature maintenance today, but really this is a system that has a pretty substantial impact on a commercial heat pump water heating system as a whole. And so we have other courses, webinars that really dive deep into the details on that temperature maintenance system so that you can address that problem in design early on and really have a reliable and a robust and efficient heat pump water heating system. And so this is serving about 200 units and has been operating for probably close to 4 or 5 years now, and helped this boutique apartments achieve LEED Platinum certification, and really drive down the energy use and the tenants' bills that are associated with that hot water load. And then once again, I alluded that we can have multiple commercial central systems. It doesn't have to be one central system for a building. And so at HopeWorks Apartments, we located heat pumps on the roof. We have our little conceptual diagram here and a storage tank below. And that served a group of units vertically. So if we're looking at our picture here on the top right, we would have a heat pump on top there, a storage tank on that level, and that would serve this bank of units. And then we repeat that. And so we repeat that multiple times so that we're serving the entire building, right? We can't forget about someone's hot water needs. So looking at the rooftop, this building had really substantial energy efficiency goals. They were going for net zero energy and are on track to achieve that, which is fantastic. So you'll see a lot of photovoltaic panels up here taking energy from the sun, converting that into electrical energy that's powering those heat pumps, as well as other devices, plugs, lights in the building. And so we are, we can locate a few of those heat pumps, and those are really just serving those units vertically. Once again, this is using the Stand-in or Sandco 2 heat pump water heater, which uses CO2 as the refrigerant, which can work down to very cool temperatures. So we can locate it on a rooftop. And we talk about refrigerant selections in some of our other courses, so I encourage you all to attend those, especially if you're working in the engineering world. So I'm gonna pause here for questions before we go on to the 4 components of our commercial heat pump water heating systems.
All right, and I'm looking here for the questions. If there's any coming in, I don't have any currently, but we can pause for a bit and see if anyone would like to comment or question within the go-to Q&A bar there, the question bar. Sometimes it takes a while for folks to type in their thoughts.
Yeah.
So Colin, we have a good class today, almost 30 folks here, which is really great to see the enthusiasm, and I'm really glad to see everybody here. And I know that there's a lot of questions about this technology, right? It's fairly unknown still, so hopefully folks are feeling free to ask. Alan writes, what's the expected lifespan of commercial heat pump water heating equipment?
Yeah, it's a great question. Definitely a common question that we get. It's relatively similar to a well-maintained gas or electric resistance water heating system. These are very engineered pieces of equipment that have been tested by the manufacturer, and so you can expect to get 10 or more years out of this equipment. Occasionally, you might push the equipment beyond its boundaries simply because of some unknown reason or misapplication of a heat pump water heater, and that will dramatically reduce the life expectancy or the duration, the operational duration of that equipment. And we definitely saw that a lot in the beginning when these systems were first being implemented, that some applications, when they're applied correctly and took account of some key considerations, worked very well and are still working very well today at a high efficiency. And other systems that were misapplied, failed right away, flat on their face. And so Definitely there's been improvements in these pieces of equipment over the past 10 years, but this equipment in general will last just as long as what you can expect to get out of a comparable gas or electric resistance water heater.
Great, thank you. So the follow-up question then from Alan is, so 10 years expected, but possibly less if it's not sized properly.
Not necessarily sized, but there's a handful of reasons where the equipment can be, pushed beyond its operational range during certain climate conditions or to meet a certain load, and that's when we see a decrease in the operational life of that unit.
Okay, here's another question from Eric. Will a larger tank size increase the lifespan?
Oh, it may, but it's not going to do it every time.
Okay. Do you have any suggestions on what will, Colin? I mean, you've outlined some things.
Yeah, so it really comes down to the climate conditions. You have to understand what refrigerant the heat pump's using and where that operational range is. So whether it can heat or provide heat to the system when it's 40 degrees out and that's the cutoff, or whether it can provide heat to the system even when it's -5. And so we have to understand that point, but we also have to understand during that event where the air is cold, what's the inlet water temperature to that heat pump? Because if we have a very high inlet water temperature and a very low amount of heat in the air, we're pushing our equipment beyond what it was typically meant to do, because there's not much heat in the air and we're trying to make something that's already hot. And so that's a challenging point for the heat pumps to operate at. So that is one of the primary failures I see. Other failures are related to cycling. So a storage tank may reduce the cycling of the heat pump when it's turning on and off, but repetitive cycling in any type of equipment definitely reduces the operational life of that equipment. And so you really want to ensure longer heat pump run cycles and make sure that they're not starting and stopping frequently multiple times or dozens of times throughout the day.
Okay. Emma writes a clarifying question then. I think this is great. We're all kind of figuring out this together. Do the skid packaged units need to be designed for specific operating conditions like space temperature, inlet water and temperature, etc.?
Yeah, so if you're working with a manufacturer that's providing a skid, you're going to want to ask them, what is the refrigerant that the heat pumps are utilizing in the skid, and what are the ambient air conditions that I can, run that heat pump in. Understanding that first will help you understand whether you can put this on a rooftop or maybe you want to locate it somewhere else where you have warmer climate conditions, or maybe you want to move to a different type of heat pump that uses a different type of refrigerant that can handle your local climate conditions. And so there's a lot of consideration there. But
working with that manufacturer is going to be key, right?
Working with that manufacturer is key. And so I can't generally say that all skids could go on a roof in Seattle. But I highly encourage you to just speak with your manufacturer, and they're going to have a lot of really good, clear guidance for you on where you can locate these technologies.
Great. And Richard asked specifically which manufacturers are offering skid mounted packages today.
Yeah, so Mitsubishi is offering one through Steffes. I believe Steffes is assembling that skid with Mitsubishi heat pump water heaters, and that's using a CO2 heat pump water heater, which can operate in very cool ambient air conditions. Nile is a manufacturer on the East Coast, and they've made skids for lumber drying for years and years, and so they are also designing and implementing skids for commercial heat pump water heating systems specifically for these multifamily building types, because it's a great application for that product. That product, some of the Niles use R134A as a refrigerant, so it's going to be struggling at those lower ambient air temperatures than that CO2 refrigerant. Yeah. And then Sandin or Sandco 2 through Small Planet Supply is also offering skids. And once again, that's more of a residentially sized heat pump water heater, but can definitely be used in a commercial application. And we've had a lot of great success with that.
Great. And Richard, I'll put in the links to those manufacturers for you so you can have that going forward. All right, Colin, those are all the questions.
Great.
Thanks so much.
Well, thanks for the questions. It's great to get that audience interaction and clarify some of your questions as best as I can. The next thing we're going to be discussing is the 4 components of a commercial heat pump water heating system. So the first thing we have is our primary heat pump water heater. This is the device that's moving heat out of the air, putting that heat into the water, and that's a very, very efficient process. It's much more efficient to move heat than it is to make heat. So that's what our primary heat pump water heaters are doing. But those primary heat pump water heaters are not instantaneous water heaters. It takes them time. They have to go through a cycle to move that heat into water. So we have typically a primary hot water storage tank. This is our thermal battery where we're storing the hot water. We also have a temperature maintenance system. And we have a temperature maintenance system in a gas water heating system as well as an electric resistance water heating system, but it might be the same as our primary heat pump water heating system. For commercial heat pump water heaters, depending on what technology you're using, you might want to separate that primary system from your temperature maintenance system. And so I'm breaking those two systems out here. But our temperature maintenance system is what's keeping the water in the distribution piping hot. And in these multifamily buildings, we have a lot of distribution piping. And so that system can definitely influence the overall system efficiency of our commercial heat pump water heating system. And then the last of our components is the controls. We have some way to turn on and off these heat pumps and maybe report alarms or trend efficiency data so that the building maintenance personnel can better understand and maintain these systems in the buildings. So we're gonna step through these one by one. And of course, we're gonna start with the primary heat pump water heaters. And so this is really our engine. This is what's taking heat out of the air, putting that heat into water. This is doing the big lift. And shown here on the screen are 3 large commercially sized heat pump water heaters that are great for a variety of different applications. We have our Colmac heat pump water heater, which is using the refrigerant R134A. We have a Nile heat pump water heater, which is also using R134A as the refrigerant. We have a Mitsubishi that's using CO2 or R744 as the refrigerant. And so our primary heat pump water heater is doing the big lift. It's taking that cold water in at 50 to 60 degrees from the city main connection and heating it up above 120 degrees, typically to around maybe 140, 145 to store in our primary storage tanks. And it's really important that we all just understand the basics of how a heat pump works, because it's not magic. We have heat pumps in our kitchen. Our refrigerator is a heat pump. We have heat pumps in our car, our air conditioning unit. We might have it in our residential home as an AC or a split system heat pump doing both heating and air conditioning. So heat pumps have been around for a while, and the cycle relies on moving heat and not making heat. And it's much, much more efficient to move that heat than it is to make it. And so on the left-hand side of the screen, I have an air source heat pump water heater conceptual diagram connected to a storage tank. And I note 4 of the components in that air source heat pump water heater and the expansion valve. And over here on the right-hand side of the screen, excuse me, I have our pressure versus enthalpy or energy content chart. And so if we step through this cycle together, we'll start with the evaporator. And the evaporator is an air to refrigerant heat exchanger when we're talking about air source heat pumps. If we're talking about water source, then it's going to be a water to refrigerant heat exchanger. But today we're focused on air source heat pumps because they're most commonly available and more readily available in a plug and play application like we're looking for in these commercial multifamily buildings. So at the evaporator, we are typically using a fan to draw air over that heat exchanger. And so that's the process where we're taking energy out of the air. That evaporator is very cool or cold because it's at a low pressure on our pressure, enthalpy diagram. And so here, this evaporator may be 20 degrees less in temperature and the refrigerant in it 20 degrees less in temperature than our air source. And so we can move heat into that evaporator even when our air source is cool and we don't think there's much heat. So that's the free energy we're getting in. And so you can see we're moving to the right-hand side on the screen here. Then we go through the compressor, and the compressor is essentially a pump. It's pressurizing the refrigerant, which is boosting the temperature because temperature and pressure are correlated here. And so we can put energy in here to essentially boost the temperature of the refrigerant. So now we increase the temperature of the refrigerant and we go through another heat exchanger, our condenser. This is our refrigerant to water heat exchanger. We're taking heat out of the refrigerant and putting it into domestic hot water. And so here we're dumping 3 units of water, or we're transferring 3 units of heating energy into that water there. So we got 2 units for free. We paid for 1 with our compressor and we can put 3 into the water. That's really the magic of the system. Then we need to expand and basically modulate this pressure on both sides of that expansion valve so that we start at the beginning of our cycle again and can extract heat from the air. So this cycle that we go through is much more efficient because we're moving heat than a gas water heater where we are making heat by simply burning a flame below water to heat it. So it's important for us to understand that this heat pump cycle is very much a cycle and not an instantaneous process. And therefore we need to consider a few things like what our source air temperature is, what our inlet water temperature is targeting, what our outlet water temperature is targeting. Because we're moving heat here, we're not making heat. And so there's typically 2 ways that the manufacturer will control this heat pump water heating cycle, either in a single pass heating cycle or a multi-pass heating cycle. And these are exactly what they sound like. Single pass will take in water at the cool temperature of maybe 50 to 60 degrees, what's coming from that city main connection, and heat that water up to our usable or above our usable temperature and store it in the tank. So in one single pass, we're taking that water in, heating it up and discharging it into our tank at a usable or above usable temperature. Multi-pass, on the other hand, will typically add about 10 degrees of heat to the water as it goes through this cycle. So it might take multiple passes or multiple cycles for that water, if it's coming in at 50 degrees, to get all the way up to 140 degrees. So here on the screen, I'm showing 110 degree water coming in and 120 going out. And you'll notice that the tank connection here is low in the tank. And in our single pass example, it's high in the tank. And that's really important. And one of the things we'll discuss in some of our deeper dive webinars, because when we get water coming in at 60, it's going to be going out at 70. And we do not want to put 70 degree water at the top of our tank. Otherwise, we're going to have complaints in our building with or complaints from our occupants in the building. So the single pass heat pump water heating system, because it's really using the full heating cycle and capturing more free energy per cycle is typically more efficient than the multi-pass heating cycle. However, the single pass heating cycle struggles to heat water that's already hot. So if this water gets above 100 to 110 degrees, it's going to struggle to put that heat into water and maintain a good operational point. That's where multi-pass heat pump water heaters really shine, is they're much better at just putting as much heat in the water as they can, but need to do it through multiple passes. And it's typically a little less efficient, but in general, the multi-pass heat pump water heater is better suited for that temperature maintenance load or keeping the water hot in the distribution piping. So that's one really important aspect of heat pump water heaters to understand, is not only what technology and refrigerant is being used in that heat pump water heater product, but also what the heating cycle is designed as, whether the manufacturer allows you to specify a single pass or a multi-pass heat pump water heater, or if their product is only suited for a single pass operation. And so there's a few considerations. This is kind of our bullet point list for us to hopefully refer back to when we're working on a heat pump water heating system, is we need an air source or a heat source for these products. They're moving heat out of the air, putting that heat into the water. So we want an air source or a heat source that is there and available at all times of the year, because we have a hot water load at all times of the year in our multifamily buildings. We also want to consider what equipment we're using and how its heating cycle is set up. Is it a single pass or a multi-pass heating cycle? It's going to allow us to appropriately design our storage tank connections and also operate that equipment in the range that it was designed to operate in. We also need to consider our electrical connections. You're typically working on a team when we're working on these buildings, and so we have to work with the electricians and other trades for these systems. And they might be making some assumptions. One of those assumptions, maybe it's a gas water heater, which typically doesn't have, much of an electrical connection requirement. It just might be a few 120, 20 amp circuits in the mechanical room. Heat pump water heaters, along with electric resistance water heaters, require more energy because for a bigger electrical connection, because we're using that to get energy into this water. And so it's important to coordinate that electrical connection and understand what equipment you're using and what voltage and phase it's operating at. The other thing that's super critical is our water connections, not only to our storage tanks, but to our heat pump water heaters. If these heat pump water heaters are located outside in Seattle, there's potential for that to freeze. So do we want to design in freeze protection, or are we going to super insulate the pipes, or does the heat pump manufacturer have some built-in control cycling to act as a freeze protection means? It's really critical that we understand our water connections and whether freeze protection or other measures are required so that we don't have issues on our cold days of the year. And then condensate management. Heat pumps are taking heat out of the air, and so there's potential for moisture to condense on the evaporator coil, and that moisture that's condensate, right? We collect it, it's condensate. We have to manage that condensate and put it somewhere. It's not acidic condensate like in our gas water heater, but we do need to make sure that if these heat pumps are on a rooftop and that rooftop is subject to freezing, that we're not dumping the condensate right on the rooftop, creating an ice skating rink for the maintenance personnel, right? We have to manage that condensate appropriately. Typically not very challenging, but something that you need to consider with these heat pump water heater systems. And then maintenance and access. These heat pump water heaters have an evaporator, which is a big heat exchanger. This is it shown on the back of a Colmac there. And that evaporator typically has an air filter on it. you can see some debris already catching on this air filter here with that white marking. So that air filter needs to be routinely cleaned or maintained, typically on a quarterly maintenance cycle. That's one of the maintenance items that is different than a gas or electric resistance water heating system. So you both want to make sure your maintenance personnel understands how they need to maintain these pieces of equipment, but also that they have adequate access to maintain it. If we put a heat pump water heater on a roof that's fairly inaccessible, or you need a ladder to get to, that's going to be much more hard or much more challenging for the maintenance personnel to access. And so they might defer that maintenance, and that might lead to future problems with your equipment. So we really want to make sure that we're designing access for these maintenance procedures, and we're not putting these heat pumps in an inaccessible area or a challenging to access area. And then one of the last most important considerations is the sound level and the noise that may or may not transfer to the nearby residences. The commercial heat pump water heating systems can range from 45 decibels to 65, 70 decibels, depending on what product you're using and how it's operating. That can be a lot of noise, and so we want to make sure that it's not directly adjacent to a residential window that's operable. We want to provide vibration isolation or other acoustic provisions to prevent vibration from transferring to the building, as well as dampen the noise being transferred as a whole to the building or throughout the building. So it's really important to consider what the noise level is for these heat pump water heaters and make sure that you're attending to that so that you're not creating a very noisy system that's just going to be a nuisance for the occupants. And I'll pause there before we go into primary storage, and we can take a 5-minute break to stretch our legs, get a fresh cup of tea or coffee, or use the facilities, and come back at, what is it now? 11:07. So maybe 11:12, 11:13-ish, and we'll start up again there. And the next thing we're going to be discussing is the primary storage, where we're storing this hot water for use in the building. So I'll see you all back here at 11:12, and we'll kick off with the discussion on the second component, which is the primary hot water storage system. Well, welcome back, everyone. Hopefully you got a minute to stretch your legs. I made myself a fresh cup of Earl Grey tea to match the color of the sky out right now. Lauren, do we have any questions that came in through the break, or should we keep moving on towards the primary storage tank section?
Let's move on. No questions yet.
Great.
Okay.
So the primary storage, I mentioned before that heat pump water heaters are not instantaneous electric resist, or they're not instantaneous heaters. So we need some place to store the hot water that we're making with that heat pump water heater. This is our thermal battery bank, our primary storage. And so what I'm showing here is a picture from a project in Seattle where we had, I think it was 5 storage tanks connected together. I guess that's 6 there, 6 storage tanks connected together to provide a larger storage volume. And this is necessary because we can trade off between how much heat capacity or recovery rate the heat pump has with how much thermal storage we have or how big our battery bank is. We can relate this to our solar systems, where typically we have a bunch of batteries connected together because it's really expensive or not possible to buy one huge battery. And so we can offset in a photovoltaic or solar, we can offset the amount of energy we're creating with the amount of energy we're storing in a solar array or solar off-grid system. And we can do that in the same way with our hot water system. We can offset or trade off between the heat capacity or the recovery rate of our heat pump with how much storage we have. And because heat capacity or the recovery rate of the heat pump water heater is typically more than traditional gas systems, we might want to prioritize more thermal storage to basically have a less expensive first cost for our system installation. And so that's why in this example, although this is, maybe 250, 300 unit apartment building, we have 6 storage tanks connected together. Each one of those storage tanks can hold about 500 gallons of hot water. And so we can use that in our favor to really reduce the amount of heat pumps we need to provide to that building to reduce the first cost associated with that system installation. So through sizing, we can really drive down the first cost of these systems, and is one way that you can really result in a more economical system or reduce the burden for the building owners or operators. And so for our low income projects, this is one way that we can definitely save on first cost, is prioritizing more storage than we typically have. So like our battery banks, we can connect those in series or in parallel with our solar system, or if it's in our Tesla or whatever electrical device we have, we can connect those batteries in 2 ways, either in series or parallel. We can do that same thing with our heat pump water heating systems, and that's thermal storage. We can either connect them in parallel, which there's some important considerations that we must take into effect, but this essentially ends up operating as 3 tanks, if they're perfectly balanced, operating as one single tank, where the cold water is coming in and it's going in equally to each one of these tanks. And the key thing here is balancing, because if there's one easy flow path and one challenging flow path, then that's when we're going to get an unbalanced system and we're going to have problems with this parallel configuration. In series, we're essentially going to connect the top of one tank to the bottom of the other. And what this does is it takes this tank and it puts it on top of this one. And so that basically stretches our thermal volume vertically. And so we can get a lot of stratification. And that's one thing that we discuss in our engineering deep dives, is when the in-series storage tank design really makes sense what some of the great advantages are for it, either from a thermostratification standpoint or controls, and how to make sure that you're not going to run into any issues. But I'm just opening this up all to us that there's two primary ways to connect our storage tanks. And if we've been operating in the gas water heating world, we're probably fairly used to seeing them connected in parallel, those gas water heaters, but not in series. And so we might be once again taking a little bit of a different design approach to really benefit the operational range of that heat pump water heater with that in-series connection.
Hi, Colin.
Hey, Lauren.
We got a couple of questions here. I apologize to Eric. I didn't see your question before. We had a question during the break, so I apologize. Eric, we'll get to yours first. And I apologize, so we're gonna go back just a little bit. Remember when we were talking about lifespan of the equipment, and you said that it depended on the inlet water temperature. I think this is a question that is related to that. Eric writes, what would be a case where the cold inlet water temperature would be hot already? Like, why would there be heated inlet water temperature? Is that a rooftop unit in the summer, or?
No, well, I guess that could be a potential. Typically our pipes are insulated, or they should be insulated, and so that insulation should prevent that solar gain on the pipe, which would heat up the water and cause heat water or already heated water to the unit. The primary way that you push already heated water to a heat pump is in the temperature maintenance system, because with the hot water circulation temperature maintenance system, we're discharging about 120 into the hot water piping, and then we're pumping it back at a slow rate so that it maybe comes in at 110 degrees Fahrenheit. If we try to heat that 110 degrees Fahrenheit water in a very cool climate condition, with a certain technology, we may run into issues there. And we saw a lot of those issues early on in these heat pump water heating designs.
Okay.
And we can cover that a little bit more in the temperature maintenance discussion, which is after this storage tank component section.
Great. So, and maybe you want to wait for this question because Emma has a question about the primary versus the temperature maintenance. And so I'll read it. You decide whether you want to postpone it. Emma writes, I'm a bit confused about the relationship between the primary storage tanks and the maintenance tank. Is the distribution drawing from the maintenance tank first, or is there a mixing valve between the two?
It depends on the system configuration, and I'll hold that question and answer it during the temperature maintenance discussion.
Perfect. Okay.
So that's a great question, Emma. You're definitely paying attention to the details. So like our thermal or like our solar batteries or our battery banks for either our off-grid solar system or our electric vehicles, whatever we're powering with those batteries, we can also connect our storage tanks in series and in parallel. And we'll cover more of these details for the engineers in the group in the deep dive, but just due to the timing today, I can't spend too much time here. But like our heat pump water heater, we had some considerations or things that we need to be aware of. We also have those with our hot water storage. So the first is physical space, the room, and the door size. This is a pretty easy one. It's a no-brainer, but I'm putting it up on the screen here because it's critical. These heat pump water heating systems, if we're prioritizing or we're trading off between heat capacity and storage, and we're prioritizing that storage, it typically takes more physical space. Also, these tanks might be taller than 8 feet tall. So we need to really work with the architectural team to design the physical room layout so that we have enough floor space for the plumbers and maintenance personnel to work in there, as well as make sure that we can get these storage tanks through the various rooms and doors down to that mechanical room or onto the roof. Vertical in our storage is better than horizontal, and that really comes down to stratification. And stratification is what I'm talking about, is the change in temperature throughout the storage tank. So very high level or good stratification is very cold water on the bottom, a very thin transitional layer of warmish water, and then very hot water on the top. We want to minimize the amount of cold water and that transitional layer. If we have a very mixed tank or very low stratification, then that middle layer, that warm layer, will dramatically grow, and that's going to be a very not great stratification. In a horizontal tank, we have more surface area, more volume for that stratification layer, and that's the reason that vertical tanks are better than horizontal, is they're increasing the stratification index or the thermal profile in that tank. We're using our tank more efficiently in that vertical orientation. And then multiple tanks in series or parallel. If you're doing a single pass heat pump water heater, you're probably going to be looking towards a series primary storage tank design. But if you're doing a multi-pass heat pump water heater, there may be reasons to do a parallel storage tank design. And so it's really critical to understand what the advantages and disadvantages of those are. And I would encourage you all to attend our engineering deep dive series to get more details on that. And then the height of the control sensor. Typically we have some aquastat or some temperature relay that's controlling the heat pumps on and off. And it's really critical that we understand how tall or how high that is in the tank, because that allows us to calculate how much unusable volume we have at the bottom and how much usable volume we have at the top. And that relates to our sizing of these systems, which relates directly to how much storage volume we need and how much heat capacity or recovery rate we need to meet a given load. And then the pipe connections, the size and locations. If we're doing a series tank design, all the water is going to be flowing through this connection here. And so we want to make sure it's appropriately sized for the entire water heating load. If we're doing parallel, then that's going to be split across multiple connections. And so we can downsize those if we need to. We also want to understand the location of these. Is this at the bottom of the tank? Is it 10 inches up? Is it 25, 30? Is it at the top of the tank? The size and the location is key to understanding really the effective storage volume here. In most designs, we want this port to be as low as possible and another port to be as high as possible or at the top of the tank. And that's going to better utilize that entire storage tank volume. And then the insulation level. We're typically storing more hot water than we do in our gas water heating systems. And that water may be at 145 degrees. So we want to insulate these as best we can to reduce those parasitic losses, right? It's the whole reduce, reuse, and then recycle. We want to reduce those loads first. And then thermal isolation. If this tank is on a concrete garage floor, we're required to insulate it with an R10 pad. That's in the energy code. So we want to make sure these tanks are isolated in some way from those concrete pads, which can basically conduct conduct heat down and out and reduce the efficiency of our storage tanks.
Really quick, Eric writes, do you ever have multiple aquastats, high, medium, and low, or does that just get too complicated?
Absolutely. We definitely do multiple aquastats, and there can be some really great advantages to that. When we have our series storage tanks, or let's say 3 storage tanks in series, we typically put 1 aquastat in each tank. And that way we can turn on the heat pumps at the second tank or the first tank to really make best use of the equipment and the load that we need to meet or ensure that we're meeting that load.
Awesome. All right, I'm going to pause till we get to the maintenance section for Jose and Emma's questions.
Yeah, great. And then maintenance and access, just like with these heat pump water heaters, these tanks are bigger. So we want to make sure that that physical space we're working on is also providing our maintenance personnel with proper access to these tanks. There are definitely maintenance procedures to storage tanks. We're not going to dive into those today, but they're, the same across what various heating sources, whether it's a gas or a heat pump water heater. There's routine maintenance procedures for those thermal storage tanks. And so we'll pause for questions here. It sounds like we don't have questions, but Emma has one on the temperature maintenance system. So I'm just going to dive right into this, and hopefully we can address Emma's questions and any others that come up. So the temperature maintenance system, let's go back a screen. I am showing a dedicated temperature maintenance system here, which essentially means that the cold water from the city connection comes in, and that goes into the bottom of our primary storage tanks. Our primary heat pumps then take that cool water and heat it up. And these I'm showing as single pass heat pumps, so the connection's at the top of the tank, and we're putting 140-degree water at the top of that tank. The hot water return from our circulation system, this is our temperature maintenance system, is connected to the bottom of a dedicated storage tank. And this is our temperature maintenance storage tank. So that return water is flowing through there into the storage tank, being reheated with our heat pump water heater. And this is a multi-pass heat pump water heater. And then that hot water, once it's reheated, when it's flowing in, some of it's flowing out, right? And so it's going out back to that mixing valve into the building. So our mixing valve is mixing both the water coming from our primary storage and the water coming from our temperature maintenance dedicated storage tank. Then it's mixing that water out to 120, goes out. Some people use it, some of it's circulated back. And there's a portion that goes back into that tank. And of course, there's a portion that goes here. And that's to achieve reliable mixed outlet temperatures through that mixing valve. So our temperature maintenance system is keeping the water in the distribution system hot. With our gas water heaters, we can take this return circulation water right back to what we would consider our primary storage then, and then this just connects to the mixing valve and out. But with our heat pump water heating systems, that can present issues, and so we want to address this through design. But our temperature maintenance system is this distribution piping, the mixing valve, and the circulation pump, and then some kind of heating source. And right here, I'm showing it as a dedicated heating source or a dedicated storage tank with a heating source in it. So this is a little bit of a, interactive kind of click through thing for us all to really understand the temperature maintenance system and its value, and how it challenges or how it presents a challenge to certain heat pump equipment. So heat pumps are super efficient at taking in cold water and making it hot and putting that in the tank. This is great, but we have to send that hot water out, and in big buildings with large distribution systems, we want to circulate some of that water continuously so that when Suzanne opens a fixture at her shower at 4 a.m. in the morning, she has an early schedule, that water is already hot in that distribution piping. It hasn't cooled overnight, and that's because it's circulated continuously. So this is really important for our occupants so that they're not draining a bunch of hot water out of the system or cool water out of the hot water distribution system to get hot water at their fixture. But returning this hot water, return water, to the tank and its continuous operation de-stratifies the tanks or mixes the tank. So here I'm showing it turn from, our very well stratified tank with blue water at the bottom, cold, thin transitional layer, and then heated water at or above temperature at the top. When we take 110-degree water back from our return circulation system, that's going to mix that tank up and put a lot of 110-degree water. so that when this heat pump is turned on now by this thermostat in the tank, it's going to pull in water that's already somewhat heated. And this is a challenging operational point for a lot of heat pump equipment. Because this water is already heated, it's trying to put heat into that water, but it's already heated. So it's challenged to operate at that point. If it's cold outside, it becomes a more challenging point because there's less heat for that heat pump to move into that water. So heat pumps in general are not very good at making that warm water hot. And that is typically that hot or that return water is coming back warmish from our hot water return or hot water circulation, our temperature maintenance system in the building. So we have a few design solutions to isolate that hot water circulation load from the primary heat pump water heaters. And we can either do this in a series swing tank or in a parallel multi-pass heat pump water heater example. And I'm showing both those throughout this presentation, but we're not going to dive into the details here just for time's sake. And I would encourage you all to come back to the engineering deep dive, where we'll spend almost an entire session on better understanding this temperature maintenance system, how it impacts our heat pump water heaters, and what you as the designer or the engineer or the plumbing contractor needs to be aware of when you're specifying or buying equipment for these large multifamily buildings.
All right, Colin, shall we delve into the couple of questions there?
Yes, let's do it.
All right. So Emma had written, I'm a bit confused about the relationship between the primary storage tanks and the maintenance tank. Is the distribution drawing from the maintenance tank first, or is there a mixing valve between the two?
So when there's a hot water draw in the building, cold water enters this pipe and pushes out hot water. That's going to make its way to the mixing valve. And in this example, it's going through an electric resistance water heater in series. We can also have the same thing, cold water or hot water draw. Someone uses hot water at the fixture, cold water comes back here. It's going to offset hot water, and that's going to go in a parallel connection to our mixing valve. When no one's drawing hot water, this pipe will not have fluid flowing through it. And so in that case, when no one's drawing hot water, return water is pushing through the bottom of this temperature maintenance tank and pushing that hot water out and into the distribution system. A portion of that water is mixing with the portion that's being reheated so that we're always sending out 120-degree water. So I hope that clarifies Emma's question.
Great. Here's another one from Jose. How effective would be an in-series storage tank with a multi-pass heat pump water heater compared to just a larger tank, or would that be similar?
I think it would be fairly similar. The challenge is if we can utilize one tank, we typically get a better use of our effective storage volume, or we get better use out of that storage tank. Using multiple tanks either in series or parallel is great to extend our thermal storage capacity. And typically we do that just because of physical constraints. But it does mean that there's pipes connecting multiple tanks and there's more heat loss in that pipe than the storage tank. So there's a little bit of a deficiency hit there. But in general, you know, if you can just do one storage tank, that's probably the best. If you need a larger storage volume, then you want to be looking at multiple tanks in series or parallel.
All right. You got it. Thank you so much. That's it.
Great. Let me click through a few of these. So really it's this return water that's warm, usually around 110 degrees, that's problematic for our heat pumps. And so we have a handful of different design solutions to address that. And I would love to spend more time with all of you today on going through that, but we don't have time in this presentation, so please come back in a couple weeks. for our engineering deep dive on that subject matter. And so the last of our 4 components is the controls. We have our primary heat pump water heaters, which are moving heat into water. We have our primary storage tank, which is storing that hot water. It's our thermal battery. We have our temperature maintenance system, which may be a dedicated system, but that's essentially reheating our distribution losses, or reheating the hot water in the pipe, the distribution piping. And then we have a control system, some system to control all those pieces, or maybe it's a controller for each individual heat pump that's controlling its own self. So there's typically 3 tiers of control interface. The base tier, we'll call, is usually the lowest cost tier, is just the heat pump water heater's internal controls. So in this case, the heat pump water heater is going to completely control themselves based on a storage tank temperature, or maybe a few storage tank temperatures if we have multiple sensors. We also can have a heat pump with some kind of BMS interface that's reporting to a third-party building management system or some other trending system in our building. And there can be great advantages to integrating our heat pumps with a building management system that's already in place, or potentially specifying a very minimal building management system that is just looking at our outlet water temperatures from our heat pumps and any alarm conditions, as well as the outlet water temperature to the building fixtures. Knowing a few points just like that can really be an advantage to our building maintenance personnel, so that they can be more proactive on keeping tabs on these systems and making sure they're running really efficiently and effectively. The other reason this can be really helpful is if you have a backup electric resistance or a backup gas water heating system backing up the heat pump water heaters. Typically, tenants complain when they don't have hot water. But if your backup system's running, you probably have hot water, so you won't get that complaint. You might notice, however, a month or 2 later when you get the energy bill, and it's 3 times as much as what you were paying for previous months. So if you have a backup system, it's really critical and important, I would say, that you tie that system in or have some kind of control logic to notify the building maintenance personnel or the operators or the construction team that the backup is running, so they can be proactive on addressing what the problem is with the heat pump and making sure that they get it up and running to reduce that cost associated with our energy use. And then the last tier of the controls is the external or third-party controls. This is a great system when you have multiple pieces of equipment that all need to work together. If we think of an orchestra, we typically have one conductor standing up there directing the orchestra. This is really what that's doing. It's having one external or third-party point that someone can go into and look at and change set points to direct that heat pump equipment and all the associated equipment that's serving that commercial heat pump water heating system. And so this is a really great and robust design, because if we have 2 conductors in our orchestra, they might conflict occasionally, and that might create issues. If we have a single point, we can reduce the potential for that to happen. This as well allows us to alter the heat pump cycles, as well as how they're staging on and off, and a lot of other capability can come with this external control interface. And so there's a lot of advantages to it. However, it definitely adds cost to the project. And so there is the potential for each and all of these systems to essentially have an internal interface that comes standard with our heat pump water heater equipment from the manufacturer. And so a few examples of just what this looks like and a few more details on it. In our internal interface, we have a Colmac heat pump water heater here. Behind this panel there is a control screen. And we can set the discharge water temperature at 143 or 145. and we can set what the call for heating is or what our inlet water temperature range is. There's a lot of potential and capability here, but we're typically not going to be communicating between other equipment in this arrangement, and it might not be reporting out all the error and email or any errors or system errors or issues in the system. The temperature maintenance system, if it's a dedicated temperature maintenance system or a dedicated heat pump water heater for that temperature maintenance system, it's likely running independently and controlling itself here too. So this is definitely an option. I think all manufacturers have a heat pump that has controls built in and is capable of doing everything necessary to provide hot water to multifamily buildings. But there are some advantages of tying this into our BMS interface to get that feedback, and that's what's really happening here. And this is typically a little bit less cost than the full BMS interface and still relies on the heat pump to control itself based on a temperature in the storage tank. But in this BMS system, we can trend the outlet water temperature, the various storage tank temperatures, the run times, and a lot more data, which can be really influential to optimizing our systems and doing preventative maintenance on this type of system. And then the last, for our really more complicated buildings or where we want to really be closely tied to these systems and the efficiency, fine-tuning them, optimizing them, and really set us up for great success is really this external or third-party controller. We want to work with the manufacturers here because in this example, the external controller is typically controlling the heat pump when it turns on and off. The heat pump's still controlling its heating cycle and a few other things, but this controller is typically sending a closed signal to it to turn on or turn off. And so we want to work with that manufacturer to make sure that we're operating within the equipment boundaries when we're utilizing this external third-party controller. But there are some great advantages here. We have one of these at a wastewater heat recovery system in Seattle, where we're taking heat out of wastewater from showers, from toilets. We have heat exchangers that are completely separating these two systems so that your domestic water is nowhere near the wastewater, but we're still capturing that energy from the wastewater. In that example, we had a sewage ejection pump, various backup equipment, primary heat pumps, temperature maintenance heat pumps, and a lot of controls to understand and diagnose and reduce the potential for issues in that more complicated system. So there definitely are reasons to look to use one of these more built up external third-party controllers when we're dealing with numerous pieces of equipment in these larger commercial buildings. And that concludes the discussion on the 4 components. Once again, we have our primary heat pump water heaters. They're doing the big lift, making the water hot. We got some place to store that in the primary storage tank. That's our thermal battery. We might have a dedicated temperature maintenance system or an isolated temperature maintenance system, and that might be a dedicated tank and a dedicated heat pump. That heat pump may be configured in multipass so it can better be suited to heat that load. And then we have a control system, some way to turn on and off these pieces of equipment so that we're meeting the load in the building.
Hi, Colin.
Hey.
So, question about the CTA 2045 port. If there is a CTA 2045 port, which I believe CTA 2045 has been renamed EcoPort, kind of easier to say. If there is an EcoPort and it's connected to a demand response program, is the port on the individual heat pump or on the system or external control system? Where does it connect in?
Yeah, that's a fantastic question. So a CTA 2045 port is basically a port that can connect to the utility to do demand response or load shift. So electricity is available on the grid for all of us right now, but we saw in Texas that, there were massive problems last year. And a while ago in California, before a lot of their utility programs, there were blackouts or rolling blackouts. It's available, electricity is readily available on the grid, but we have to essentially use it when we make it or generate it. Heat pump water heaters are really well suited to basically load shift because we have these thermal batteries. So we can align the time of use the heat pump water heater runs with the time of available solar energy on the grid. And that can dramatically reduce the cost of energy, because in places like California, we have time of use pricing. Basically, electricity varies in price depending on the time of the day. So there's great potential there, but we need some relay with the utility to understand when we should be doing that or when we should be not heating our water. So that's what the CTA 2045 port does, is it's a communication port between the heat pump water heater equipment or the system and the utility, so that we can load shift, load shed to really make best use of the electrical energy on our grid at a given time. Now, whether that port is on the actual equipment or on a system controller is very dependent on the manufacturer. I think right now most of them are on the physical piece of equipment, but I can see that with these skid systems that are designed for, let's say, a 100-unit apartment building, instead of having multiple heat pump connection points, there might be a single point of connection to that central controller that's controlling all the heat pumps. But this is CTA 2045 is still fairly new in its infancy, and so I can see that kind of being developed and changing along the way. But typically, I would say it's at the heat pump itself.
Okay. Alan writes, do most commercial heat pump water heating systems contain multi-stage or single-stage compressors?
Most of them are single-stage compressors. Because when we put compressors in series and have multiple stage compressors, we reduce the efficiency.
Okay. All right. That's it for questions for now. Thanks, Colin.
Great questions. So looking at our components, through a case study, we got about 10 minutes to go through this. We have our primary heat pump water heaters. This is the Jackson apartment building, new construction in Seattle. They're located in this underground parking structure or mechanical room in an underground parking structure. We have our primary storage tanks. Over here, we have 3 storage tanks, and these are connected in series. So we have number 1 way in the background there, connected to number 2. Number 2 at the top connected to number 3, and then number 3 feeds out to the building. We also have a temperature maintenance system, and this is a storage tank that we specified with an electric resistance element for backup. So it's a electric resistance water heater, but we do have a multi-pass heat pump water heater connected to that. And so the control logic there signals the heat pump to run first, and then if that heat pump ever has an issue or failure or can't meet the load, that's when the backup elements at a lower set point would engage to provide that backup heating to the system. And then we have a control system. And because we were trending the data here at Jackson Apartments to really determine how efficient the system is on a whole, we provided a third-party controller and worked with Colmac and Johnson Barrow, the distributor, excuse me, of these heat pumps to ensure that that control system is set up well and not pushing these Colmac heat pump water heaters beyond their boundaries. And we'll flip through a few slides there, pause for questions, and I'll take your questions throughout this case study, of course. But here's some info on the project and a architectural rendering of the building, along with a photo of the actual building after construction. This building achieved LEED Platinum. They did some great features beyond the heat pump water heaters located, both from aesthetic standpoints, making this really feel like a local prairie, as well as from the building envelope and other energy recovery ventilators in the building, as well as heat pumps for space conditioning. And so this building was split into 2 wings or two buildings, the east and the west. We have our east building here. We're looking north in this picture, and our west building here. And we have a central heat pump water heating system serving each of those buildings independently. There were earthquake expansion joints between the two buildings and a few other design restraints that's pushed us to essentially design one central heat pump water heating system to serve the west, and another one, or to serve the east, and another one to serve the west. And this is, of course, a mid-rise multifamily building totaling about 532 units located in the central district of Seattle, Washington. So at this project, we utilized Colmac heat pump water heaters that use the refrigerant R134A. And R134A refrigerant doesn't work below about 40 degrees Fahrenheit. In Seattle, it regularly in the winter gets down to about 23 degrees Fahrenheit. That's our design temperature. So 23 is, of course, less than 40. So if we put our heat pump water heaters outside, there's going to be portions of the year or certain days that we're not going to be heating with those heat pump water heaters because it's just too cold for them to operate. So what we did, because the CO2 heat pump water heater technology wasn't available when we were designing this project, which can operate at those lower temperatures, is we used that R134A technology, which is limited to about 40 degrees Fahrenheit, and put them in an underground enclosed parking structure. So you can see that here. So that this is a ventilated parking structure, of course. So there's garage exhaust fans running continuously, and those are pulling air, outside air, around 23, 25 degrees on our design day, into the garage and pulling it down through multiple stories of our garage. In Jackson Apartments, we go down about 2 stories, and then that air is pulled into the mechanical room by the heat pump water heaters. They take that heat out of air and discharge it to the environment. And because we have a lot of ground contact that's uninsulated and big thermal masses with our slabs and our ground, this 25-degree air is warmed up to about 40 to 45 degrees before it enters our heat pump water heaters, even on the coldest day of the year, even when we have had a week more of consecutive cold weather days. Ecotub has been implementing this design solution for at least 10 years throughout Seattle, and we've put temperature sensors in a variety of different multifamily buildings with enclosed parking garages. This is a really great way to utilize some of the underused corners of our parking garage, as well as provide a buffering effect on that ambient air from outside so that we can run these heat pumps the entire duration of the year. So looking at this system from the floor plan point of view, after the air comes into the garage, it goes down a few stories and is simply pulled through a ventilated door into our mechanical or plumbing room. So this is like a fancy chain link door, but essentially it's a very open path for the air to be pulled through. That air is then drawn in by the heat pumps when they're running. The heat pumps take that heat out of the air and discharge cool air back into the garage. And there's a system of garage exhaust fans right about here, just outside this page, that are then exhausting that air outside the building. These heat pumps could also be directly ducted to the outside of the building, but in this design to reduce ducting and to reduce first cost, we just discharge that cool exhaust air at that garage exhaust fan system, which is typically operating, or which is operating 24/7 at a lower volume, and then peaking to a higher volume or a higher airflow rate when we have toxic chemicals in the garage like CO or NO2. So here we need some ventilation openings, and I noted a few of those there that you can look at. And our domestic hot water room, to give us an idea of the size, the scale, this is about a 200 unit apartment We needed about 740 square feet to make this system work and to have plenty of access and for our maintenance personnel. And then also, I typically get a question about electrical capacity because these are heat pump water heaters, and so they're drawing electricity. And so at this project, with electric backup, which that was the owner's decision that they wanted to have a full redundant electric backup system here, we're looking at about 87 kilowatts, or about 540 watts per apartment. Without that electric backup, we're going to significantly reduce that down to about 31 kilowatts or 190 watts per apartment. So some maybe rules of thumb, probably not rules of thumb, but some general guidance there on sizing both our air terminals for mechanical and our electrical system for any electrical in the group today. And so here's another picture of our system. You can see some temperature sensors up here. If you look carefully, there's a temperature gauge, as well as a flow meter back here, because like I said, we're trending the data here at Jackson Apartment. We have that BMS system that is logging a bunch of data points, whether it's temperature, flow, or electrical power in, so that we can calculate the true efficiency of this heat pump water heating system. There's two primary heat pump water heaters connected to some storage tanks. And this is in that buffered garage space because of the R134A refrigerant being used. CO2 has recently come on the market in commercially available products with Mitsubishi, and that can operate down to about -5 degrees Fahrenheit. And so there is, in that case, that heat pump water heater could definitely be located on a rooftop in Seattle and provide heat to the system year long. Sanco 2, another CO2 manufacturer or heat pump that uses CO2, can also be located outside in Seattle and run smoothly all year long, even when it's snowing outside. And so looking at our temperature maintenance system, we have this electric resistance tank, which is acting as our temperature maintenance storage tank. We made it an electric resistance tank because the owner wanted full backup. And so that's how we are backing up this heat pump water heater, which is our temperature maintenance heat pump water heater. You can see that it's smaller than our primary heat pump water heaters because it's serving a smaller load. It's also located outside this room because there's a manufacturer update or a product update when we were working on this. This was originally in that room and ducted out, but because the update put this fan on a hinged access door, we would have to disconnect that fan and the ducting from it if it was ducted in the room every time we needed to open this panel to get maintenance access. So we simply just put this one outside the room to prevent the requirement from ducting it if it was inside the room. And this is a 410A heat pump water heater too, so it's better suited for that multi-pass heating cycle, as well as it can operate at lower air temperatures as well. So there's some benefit there, or some reason why we could locate it outside. And so here's that architectural rendering or image, a little bit bigger, blown up, where you can see we're drawing air in, goes through a few levels of the garage. The heat pumps are blue cylinders here, pull heat out of the air, discharge it either towards the garage exhaust fan system or directly into the garage exhaust ducting, and that makes its way outside the building. That operates continuously. We store hot water in the storage tanks, and then that's sent out to the building. We do actually get some free energy from cars because cars have engines. Engines are hot. So every time a car drives in, we're getting a little residual heat there too. But the primary buffering effect comes directly from this enormous amount of ground contact here. And so I hope today, going through a lot of information on these commercial heat pump water heating systems for multifamily buildings, that you all realize that these are great systems for all building types and applications that use hot water or that have a hot water demand. In our residential buildings, we typically have a much higher hot water demand than, let's say, in our commercial office building. So there is even more reason to do it in these multifamily residential buildings to really achieve that higher level of energy savings. And depending on what type of equipment you're selecting, how that equipment is sized, whether it's residentially sized or commercially sized, and what the building architectural and layout is, there's good and better solutions for all building types. It really comes down to the design and implementing the right design solution for a given building type and application. And I mentioned before that manufacturers were starting to provide more skid systems, less of this custom engineer solution that I just walked you through with the Jackson Apartments case study. And so these are 3 of those skids that I mentioned earlier: Mitsubishi Sanko 2 with the water drop from Small Planet Supply, and Nile, an East Coast manufacturer. They're looking to bundle these up in a skid that take a reliable design approach and heat pump water heater configuration, storage tank configuration, package that all up so that we can reliably and effectively install as many of these systems as possible to dramatically reduce the electrical load across the nation associated with domestic hot water heating. Save us all money and energy in the end. And so I will happily pause for questions here and take any, while you all can take some time to share any key takeaways from our presentation today. And it looks like I went a little bit over, so I apologize for that. But we're happy to take a few questions here before signing off for the day.
Yeah, Colin, you and I have been on these educational sessions for a while now, for a good part of the year, and I know that I'm didn't know much about these systems before I started, and they really are kind of a complex. They're a little more complex than meets the eye sometimes, and I just really enjoy hearing you talk about them and making what seems very complex very straightforward. So kudos to you for making it understandable, and Emma writes great presentation, and I concur. I always enjoy hearing you teach and making these systems understandable. We don't have any questions coming in. I think we've addressed several of them as we've gone through. We do have one from Alan. This is interesting, and I'll be curious as to your thoughts here. Have European nations moved to commercial heat pump water heating systems, or do they still predominantly have natural gas?
Great question. Yeah, a lot of these products have been used in European nations for many years now. We are actually behind the game here in the United States of America. Believe it or not, we're not leading the charge on the commercial heat pump water heater front. Sanko 2 and Mitsubishi are both non-US manufacturers, but there are manufacturers in the US, Colmac, Nile, A.O. Smith, Rheem, that all have these technologies available. And they've had it available for a few years at least, if not many, but there are probably more heat pump water heating systems in European and other countries than America. Yeah,
I know Asia, China, Japan, a lot of countries on the Asian continent have a lot of commercial heat pump water heating systems.
Yeah, it's their standard practice there.
Yeah, yep. All right. Well, thank you, Colin. That's the end of it. I'll let you wrap up. Thank you.
Great. Thanks again, everyone, for coming. Appreciate the positive feedback, and look forward to working with any and all of you out there. Ecotop's a great engineering firm, and we're always looking to work on new and exciting projects. We do a ton of really highly efficient, pushing the energy envelope beyond what's normal. So looking forward to working with all of you today out there, or supporting you in the field if necessary. And thanks for your time, of course. And I did mention that we have some additional courses. One of them is the Engineering Deep Dive, which is two 2-hour seminars on January 11th and 18th, so early next year in 2022. And so I'd love to see as many of you there as possible. And we will definitely dive into way more details on the heat pump water heaters and the refrigerants that are in them, refrigerant selection. We'll look at sizing, the Eco Sizer program, which is a great program to help you size your commercial heat pump water heating system, as well as the temperature maintenance system, and spend a lot of time on where we at Ecotope have run into issues and how we've addressed those issues through standard design practices with a dedicated temperature maintenance tank. Thanks for all for joining, and I will sign off here now.
Thanks, Colin. Thanks to everybody. Bye-bye.